Please start.
Yeah, hi everyone. Thanks for giving us this opportunity to present our work. This research was conducted by our Spark Lab at New York University Abu Dhabi with our industry partner, the ALEC Engineering Contracting and the Hilti from the UAE region. Our topic is implementation of a robotic system for overhead drilling operations, a case study of the Jaibot in the UAE. As indicated in the topic, this research presents a case study of an on-site construction robot for drilling operations. On-site robots seems to be a hot topic for construction industry. However, previous research on testing such robotic system rarely happens on the real site. Besides, there were no consistent method to sufficiently analyze the efficiency of the robotic system. To help solve these kind of problems, this research uses a case study to conduct a comprehensive feasibility analysis to assess the drilling robot, and then we proposed a systematic framework for robotic management to get the future usage of such systems. The feasibility analysis model consists of 3 key elements: the project description, performance criteria, and human factors. Robot descriptions help us understand the capacity and the functionality of the robot. Task characters shows principles and the basic workflow. For the performance criteria, we refer to the conventional criteria such as accuracy, productivity, health, and safety. And then besides, we took the human-robot factor into consideration. We would like to investigate the changing roles of human workers and their attitude towards this kind of changes. In next few slides, our industry partner from Hilti will give you a general introduction of the Jaibot robot.
Thank you. Hilti Jaibot is a semi-autonomous robotic drilling that covers mechanical, electrical, plumbing, and installation workflows. It is steered by a remote control that is operated by an operator to move it from one location to another. Once it is stationed in its drilling area, it will continue to drill holes automatically. It is referenced by Robotic Total Station that comes with it, Hilti PLT 300, and it is a fully cordless operation with integrated vacuum cleaner and dustless dust extraction accessories. Maximum ceiling height for Jaibot operation is ranging from 2.65 up to 5 mm, and with a drilling accuracy between 4 and 5 mm minus and plus. What it does is it drills holes repetitively, overhead drilling. It does overhead drilling for repetitive sessions between 6 mm to 16 mm up to 100 mm depth. It's fully cordless operation, like I mentioned, for 8 hours and recharge time of 6 hours. If you want to continue Jaibot beyond 8 hours, then you can do so by plugged to a power source. Its weight and dimensions are easy to fit into in terms of its weight and dimensions, it is easy to fit into a passenger hoist to move across the floors. What Jaibot does basically is to transform a manual workflow into a digital one, hence increasing the productivity and efficiency in the job sites. All the workflows start initially with a digital plan that normally would transfer into a paper plans. However, with Jaibot, you export it from a Rivet or AutoCAD and upload to Hilti Cloud. Then once Jaibot is stationed on the job site, on the floor, you would download the drilling points via this integrated SIM card and the PLC 400 tablet. Prior to the operation on the job site, control points have to be marked, and Jaibot should be referenced according to the Robotic Total Station Hilti PLT 300, so that Jaibot would know where it is located according to the walls and columns in the job site. It is basically like the eyes of Jaibot. During the drilling, you could download at any point of time any reports and share with all the assigned user and stakeholders. If you can see in the picture, above the Jaibot picture, you would see some markings on the ceiling. Jaibot does not only drill, but it also marks for the installer to know which service installation he should be doing for that hole. It's a dice system, so it would spray paint right after the drilling, indicating the hole specification. When it comes to the drilling performance in the job site in comparison to traditional methods and semi-traditional method, these are the results we would be seeing. If you're drilling into a concrete without rebars up to 40 mm depth with 2 workers with manual layout, traditional layout, and traditional drilling with building a scaffolding and going over it, you would achieve 2 workers would achieve 60 holes a day. If you move to a digital layout, but still manual drilling, 2 workers would achieve 160 holes a day. However, with Jaibot, with fully digital layout and fully automatic drilling, with 1 single operator, you would be achieving more than 400 holes a day, considering that all the situation is in favor, such as there is no accessibility issues to the floor. There is no building materials laying on where the drilling area is. Transport between the floors is made easy. The availability of the operator, availability of the digital input in terms of drilling points, marking the points on the floor. When you provide all these circumstances, Jaibot would achieve more than 400 holes a day. Hilti Jaibot was officially launched in 2020, October. However, prior to that, we were given the chance by ALEC to test it for over a year in their iconic project, Vanzabil. So now I will hand over to Tyron from ALEC to give you more insights about their iconic project, Vanzabil, and the Jaibot scope. Thank you.
Thank you for the introduction and detailed information, Pinar. For this case study, as you can see, the Vanzabil project was used. This building serves as a multifunctional 2-tower structure with what is now the world's longest cantilever interconnecting those 2 towers. The project will have hotels, offices, residences, various restaurants, spas, and will also include a pool on top of the cantilever. And of course, with ALEC as the main contractor and Alemco, ALEC's MEP leg, as Tower A's MEP lead, the project saw multiple innovative solutions being pushed onto it to improve both work quality and productivity. One such initiative is, of course, the Hilti's Jaibot, which was used for complete overhead drilling of the MEP operations. As you can see, the work was taking place on an ongoing construction site, and therefore there was numerous operations underway with multiple subcontractors completing packages in parallel with one another. This therefore meant that the robotic drilling to be done could not be done on areas already seeing the completion of other packages. However, ALEC was able to predefine 4 levels of Tower A to be drilled robotically before those other packages were in place, to the entirety that the other levels were seeing as well. The floors and subsequent areas required only 2 differing diameter holes to be drilled for the installation of their differing packages, with those holes, with the completed holes as shown on, or the numbers of those completed holes shown on screen. The system recorded details of each hole drilled, such as location, depth, diameter, as well as other information. It also recorded the status of each hole, which holes have been drilled, which have yet to be drilled, which cannot be drilled due to obstructions. This was all displayed graphically in space to easily identify the holes, and this can be seen alongside in the image on screen right now. All this information could be observed in real time. All this information can be observed in real time on the dashboard provided by Hilti. And from an accuracy aspect, the drilling diameter of the hole saw no deviation, as the robotic drilling operation is strictly linear in the Y-plane and perfectly perpendicular to suit the site's needs. Factors that did influence the robotic drilling included calibration errors in the total stations, errors from ceiling sensors, and also, of course, human errors that came from the robot's control. For instance, planning and communication errors led to deviations between as planned BIM and as built coordinates, which impacted the robotics accuracy. Focusing on the productivity side of things, in the early stages, an experiment was conducted in the basements to compare traditional methods versus the robotic method. The outcome of this experiment showed that the robotic method was far quicker than the traditional method, as it did not need any setup of ladders, marking out, or the hand drilling of those location holes. The robot could easily find the location reference from the predefined control points that were set up beforehand, using those BIM drawings, allowing it to easily identify which holes need to be drilled and where, resulting in high accuracy and, of course, high efficiency. Due to this, the slight increase in cost per hole is completely absorbed by the significant increase in number of holes that can be drilled in the same time, or in the same that can be achieved. I'd like to now hand back to Mr. Hui to complete the remainder of this presentation.
Thanks, Tyron, for the information. However, during the real site execution, the productivity was not as good as expected. The deviations come from multi aspects. For example, the current workflow is not as smooth as expected. And after we dig into the statistic, in the figure, we could see a similarity in the trend between the operation hours with the production rate. We calculated the correlation coefficient, which shows a strong relationship, indicates that the longer operation will result in a better productivity. Many reasons could cause this kind of phenomenon. For example, open area that is easy for the robot to transform, or the drilling position is easy to access with less failure or skip. For the health and safety factor, based on the feedback from the contractor, the Jaibot is quite reliable. It can improve task economics and provide a safer working environment. To find actual information of the Jaibot, we conduct a questionnaire. Oh, okay, sure. And currently, based on the practice with our partner, we summarize the basic structure of an integrated robotic management framework. The framework contains many elements in different steps, and here is the basic structure of the framework we proposed. In conclusion, we proposed a feasibility analysis procedure and integrated it into a general management framework. For future studies, it is planned that the Jaibot would be used in other projects. By adding, we could get access to the first-hand data to verify the framework we proposed and advance it to a more general one. Besides, in future work, we will adopt a past correlation estimation to give different weights to the factors that was identified in the feasibility model. That would help us to understand how different factors influence robotic adoption on the real side. This is our presentation. Any questions? We are open to answer your questions.